Now, an interesting thing happened in 1900 that I think is very worthwhile talking about. Lord Kelvin, who is the Kelvin of the Kelvin temperature scale, gave a speech. And he basically claimed that current thermodynamic understanding basically explains everything that's known right now. And there really wasn't anything else to figure out in the world except for a couple of what he called clouds. And the first cloud is what they called the failure of the Michelson-Morley experiment. Now, we're not going to talk about this, but this led to special relativity, which is Einstein's thing, and it's huge. And just realize, anyway, I'll talk more about it. But the one that we're going to talk about is more the inability to understand what's called blackbody radiation. And he thought that, well, there must be something weird going on there, but it'll be figured out soon. And this led to quantum theory, which is where we're going. And so Lord Kelvin was a powerful scientist, but he was trying to discourage people from going into science because he thought, everything's figured out. And he was so wrong. All right. I just cannot underestimate this enough, how wrong he was. So pride goeth before a fall. All right. He definitely should have just kept his mouth shut on this one. He really did think in 1900 that basically science was done. All right. There are going to be little, kind of nitpicking database things to do, but nothing like large and very, very incorrect as it turns out. So just realize scientists should always be a little modest. All right. Just kind of go with the flow, see what happens, but don't start saying that science is done because that has not been seen so far. So let's talk about blackbody radiation. In physics, you'll talk more about the Michelson-Morley experiment, but we're going to talk here about blackbody radiation and how it led to a brand new field, quantum theory, which is huge. Anyway, as you can tell, I get a little worked up over Lord Kelvin's speech. So what is the ultraviolet catastrophe? All right. If you start to heat metals, especially up, you heat them more and more and more, and they change different types of light. Like at first it's like a red light, then you can see kind of like a blue light and even a white light. And so they found that the energy of the light emitted was relative to temperature. So you'd think and stuff that you would keep heating something up and you'd keep having more and more energy come up. Well, what happened is that as you kept increasing the energy, there became like an ultraviolet maximum amount. And after you got to that point, then there was no other light, and it actually began to go down. And classical physics predicted that there shouldn't be a maximum intensity. So this is the catastrophe. Light was not behaving like classical physics predicted. Classical physics thought it should just keep going up, 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 up. But what they saw, you can see right here, is that there was kind of like a maximum, and they changed the temperature, and there was always a maximum, and then it went down, and nobody really understood what was going on.
A metal bar, like all objects at room temperature, emits infrared radiation. When heated to a relatively low temperature, however, the emitted radiation is in the red portion of the visible spectrum. As temperature increases, more light of shorter wavelengths is emitted until the bar glows white hot. In general, the hotter an object, the shorter the wavelength of light it emits. As the bar cools down, its glow returns to red.
So white hot just means that basically most of the light is in the ultraviolet region. And again, they expected that you could keep heating these things up and you'd have more and more and more energy. That's not what classical physics predicted at all. And so that was the catastrophe. It blew their theories. It blew their predestined idea of what was going on. Max Planck was a scientist around this time, and he came up to a way to predict what was happening. And he predicted and proposed that object can gain or lose energy, by absorbing or emitting energy in quanta. And a quanta is like a small packet of light. And when he proposed this and he worked through the theory, it worked out really well. And he found that basically each packet of energy is proportional to the frequency. So E equals H times nu is sometimes called the Planck energy equation. You don't have to use that or anything like that. But this allowed him then to figure out what was happening in this ultraviolet catastrophe. So this is going to be an equation we're going to use a lot. Nu is the frequency, how many waves are going by per second. And H is called Planck's constant, and it's a very, very important number to know / memorize. Most of the time when you use the speed of light, to be honest, you are using Planck's constant as well. Planck's constant is very small. It's 6.626 times 10 to the minus 34 joules seconds. Notice it's joules times seconds, not joules per second. But when Planck did this, you can see in the left-hand corner, lower left-hand corner, Rayleigh-Jean's law was what they tried to use to predict what was happening to these metal bars that were being heated up, and it was totally a failure. The dots show what was actually observed when they heated it up. Well, Planck's version, which used Planck's constant, and by the way, it was named for him afterwards. He didn't name it himself. Planck's constant fit it perfectly. All right. And that was just fantastic. So Planck wasn't totally sure why this worked, but it did work, and that was fantastic. And again, he introduced this idea how radiation can be not a continuum, but kind of in little packets of energy. And the packets of energy, which are where the frequency comes from, you can figure out the energy that is associated with it. So Planck solved the ultraviolet catastrophe that Lord Kelvin was babbling about. He didn't quite understand how it worked, but it did fit the data, and that's a lot of times the first step to figuring out how this stuff all works. E equals h nu is Planck's equation, and if you substitute for frequency equals speed of light divided by lambda, the wavelength, you can also have E equals hc over lambda. And this is kind of cool because you can see how frequency, nu, is proportional to the energy E. So what that means, frequency goes up, your energy goes up. Frequency goes down, your energy goes down. But you can also extend it to wavelength, but wavelength is in the denominator, the bottom, and energy is in the top. So as wavelength gets bigger or larger, the energy goes down. On the other hand, you have smaller wavelengths goes down, the energy goes up. And this will be important for you to kind of rationalize here what's going up. So large wavelengths, which have small frequencies, have smaller energy. And likewise, if you have a smaller wavelength, which is a larger frequency, you're going to have larger energies. And again, both of these now will use Planck's constant, 6.626 times 10 to the minus 34 joule seconds, and the speed of light, c, 2.998 times 10 to the 8th meters per second. So here's a question you might see. It says, which of the following wavelengths represents the highest energy? Now, wavelength is in the bottom and energy is in the top. Those are called inverse relationships. So as one goes up, the other one goes down. So if we want energy to be the highest, that means we want wavelength to be the smallest, okay? Now, of A, B, and C, A and B are wavelengths. They both have lengths with them. Hertz is a frequency. So that's not a good question. That's not a good answer here. That would be a frequency, not a wavelength. But the smallest wavelength would be the nanometer version. So 47.1 nanometers is the smallest. That would be 47.1 times 10 to the minus 9th meters. You can figure out exactly what that is. That's a pretty small wavelength. That should have the highest energy. So it's an opposite thing. Frequency, direct, but wavelength is opposite. Planck was one of the people that was told not to go into physics. Everything's known, said Lord Kelvin. Thank heavens Planck didn't follow that. The Max Planck Institute in Germany is a big research institute that's named after Planck. So Planck really rocked science, and that's why I'm kind of cynical when it comes to Lord Kelvin. So just kind of do your thing. If you feel like you should go into science, you should, all right? Enough said.